Hello and welcome to this lecture. We saw a whole bunch of definitions describing subspaces. Subspaces are going to be spanned by a set of vectors, right? And those vectors could be a spanning set. And then we defined basis as a linearly independent spanning set. And there we got into a solid place, because any basis will have the same number of vectors, and that became a dimension, and dimension is going to be less than or equal to k. So now how do you do computations with these things? Suppose somebody gives you a subspace as a spanning set. How do you work out a basis? Once you work out a basis, how do you get a simplified version of the basis with which I can answer questions like membership and all of that? It turns out these kind of questions are connected intimately to solving linear equations. All of that we are going to see. So this computation based on elimination is a very, very important idea in understanding subspaces. So let's get started. So somebody is giving you a subspace S as a span of V1 to Vk. And this is all of them. We are in Fn. Remember, F could be R or C. The spanning set is V1 to Vk. The question is, how do you find a basis? The answer is very simple. You eliminate starting with V1 to Vk. Okay, you start with V1 to Vk and you eliminate, you get a basis. We have seen that already, right? When you eliminate, you get another set of vectors with the same span as the original one, but they are linearly independent. That is the exact definition of the basis. Okay, so here is the form here. So you start with V1 to Vk, you eliminate, you get U1 to Ur. Then you may have done column permutations, you have to undo those. Then you get U1 tilde to U1, Ur tilde. The spans are exactly the same. So U tilde are permuted versions of U. Okay, and this gives you a linearly independent set, and that is also a basis. Okay, so U1 tilde to U1 Ur are linearly independent, and the span is the same. So basis of S is U1 tilde to Ur tilde, and the dimension is R. And not only that, this basis has a simple upper triangular form. Okay. So using this, you can answer a lot of questions easily, as we will see later on. Okay, so elimination helps you determine the dimension of a subspace, find a basis for the subspace. Not only that, it gives you a simple basis in an upper triangular form, okay, which is very useful. In fact, you can go one step further. Okay, so we got an upper triangular form for the basis. This is what I've captured here. I described that in the previous slide. You can go from upper triangular to an identity matrix form. See, notice you have all these non-zero values here, right? You can eliminate these non-zero values further, one more step of elimination, and make these values also 0. This you can't do anything about, but these values you can make 0. How do you do that? Here is the elimination that will accomplish that. Okay, you replace U1, right? U1, which is 1 followed by a bunch of possibly non-zero values, right? U1, 2, U1, M, etc. Notice what I am doing here. I am going to use these identity and cleverly make sure that all of these guys can be made 0. How do I do it? I replace U1 with this U1 prime, which is U1 minus U1 2 times U2 minus say U1 3 times U3, so on till U1 R times UR. I have only up to R, right? So up to that I will replace. Now what will happen there is, this will be 1, right? You can't do anything about it. The second term will go off to 0, right? I made U1 to U2 and I subtracted from U1, right? So second term will go to 0. Likewise, the third term will go to 0. Fourth term will go to 0. Everything up to R will go to 0. After R, I don't know. Okay. So here is a crucial, nice little idea where you're going to replace it this way and get down to zeros for on the right hand side also. Now I can proceed further. I'll replace U2 with U2 minus U2 3 further down. Okay, from U2 I replace like that. I get a 0, 1, 0, 0, 0 up to the rth position, and then I don't care what I get after that. I may get non-zero values. Now I can proceed and so on all the way up to UR minus 1, and then I'll have zeros instead of these stars. So when I finish there, I will have this U1 prime to UR prime, where you have 1, 1, 1, 1, 1 here, zeros on the right, zeros on the left, and then you will have a bunch of guys here which could be 0 or non-zero. So from an upper triangular form for the basis, we have moved to the identity form for the basis. These zeros here I'll throw away, I don't really care, right? So I don't want these guys to be hanging around anymore. I only have a basis which is a identity form. So clearly now the span of V1 to Vk is the same as span of this U primes, but I'll have to do this tildes, right? I have to undo any column permutation I may have done. So I get my same span. So the same dimension, same basis is obtained, same subspace is obtained. But you have a very, very simple form for this basis. So recall this. This will be very, very useful later on when we try to solve linear equations, when we try to find range, null of matrices and all of that. So this kind of thing in elimination is very, very important. So, notice how we are able to simplify the basis further. So, when you have a very simple basis, you can understand the subspace much better than a much more complicated basis. Okay. So, here are a couple of examples. This is the last few examples we are going to do. I think we did this earlier also, but nevertheless, it is good to go back and revisit this example and understand how the simplified basis comes along. Okay. So, here is this example I did here 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, right. So, we did this simple little manipulation and we came to this form. Okay. So, how do I get to the further simplified form here? So, from here it is very easy, right. So, from here I am going to go to, right, R2, R1 being R1 minus 2 times R2, isn't it? 2 times R2. So, R1 becomes R1 minus 2 times R2. So, I will get 1 0 here, minus 1 here, minus 2 here, and then I will get everything else remains the same, 2 3 0 0 0 0. So, you see here this is my simplified basis, this becomes my simplified basis, right. So, these two vectors, and they have the same span as before, and they have a very simple form where you have this identity form here, and then you can answer a lot of interesting questions with this. Okay. So, the other example we had, it came all the way here, right. So, this was my so called basis, but I was doing a lot of column simplifications here. So, let's keep track of it. My original set of vectors v1, v2, v3, v4 were here. Okay. I did a column permutation between 2 and 3, and then I also did a permutation between 3 and 4. Keep that in mind. We have to undo those, but then let's go to the simplified basis here. So, if you want to go to the simplified basis, I will have to say R1 is R1 plus R2 plus 2 times R3, right, and then I will have to do R2 is R2 minus R3, right. So, if I do that, I am going to get a very simple form where I will have 1 0 0 0 1 0 and 0 0 1. Notice how easy this is becoming, right. So, everything else remains 0. So, this does not matter at all. Looks like my basis is like this, but that is not really my basis, right. I do not know if that is my basis. So, actually I have to permute, right. I have to permute. I have to do, I did C3, C4. So, I will have to exchange these two first. Okay. So, if I do that, I am going to get, maybe I will keep it this way. So, if I do that, my basis will become 1 0 0 0, comma, I have to be careful when I write this down, 0, C3 and C4 I am exchanging. So, here also it does not change anything, but here it will change something, right. My first exchange C4, C3 exchange is going to do something here 0 1, okay, and then I have to exchange C2 C3, right, that also I have to exchange. So, my first guy remains the same and the second guy goes to this guy and the third one goes to this one. Okay. So, basically the span of this is exactly the same as the span of my original 3 vectors. What was my original 3 vectors? They were here, right, v1, v2, v3, v4, right, 0 0 1 1, minus 1 0 these guys. So, let me be a little bit lazy, I will do my little lasso trick here to get my whole thing covered. Oops, that's okay. Copy, come here, paste. Okay, so you come here, I can erase this guy. Okay, so my span, is this still on lasso? Okay, so my span of these guys. So, I want you to see how simplifying this is. You think there are 4 vectors here and you are doing span here and all sorts of, looks a bit crazy, but these two are the same. The span of this is the span of this. Notice how easy this basis is to describe the subspace. I can put any coordinate here. The second coordinate has to be 0. Third coordinate can be anything. I am sorry, why did I put a 0 here? This is 0. Third coordinate can be anything. Fourth coordinate can be anything. So, this subspace, which looks a little complicated, is nothing but an arbitrary element in the first, third and fourth coordinates. I can pick any coordinate, second coordinate is 0. That is the subspace. So, notice how easy it is to describe the subspace when you do the elimination, and the simplified basis is very, very useful. Okay. So, hopefully you are convinced that elimination is a very important tool in understanding subspaces, spanning sets, basis, dimension. More than anything, getting a simplified basis for your subspace which helps you solve problems. Okay. Thank you very much.